Our world runs on electricity. It powers our homes, our cities, and our ambitions.
Every flick of a switch, every glowing screen, every hum from a server farm, it's all part of a massive electrical network.
But have you ever stopped to think about what actually connects it all? What are the veins and arteries carrying the lifeblood of our modern age? It's easy to overlook. We see the final product every day, a simple, flexible, plastic-coated wire. But the journey to create this essential component is one of the most precise and fascinating stories in manufacturing. It's a story of incredible transformation, immense power, and microscopic precision. And it doesn't start with a plug, but with a massive piece of solid metal. It all starts with this, a huge, gleaming coil of raw copper, weighing thousands of pounds.
And it ends with this, a perfectly coiled, insulated electrical wire, ready to be installed in a car,
A data center, or the walls of your home. So how do you get from one to the other? How do you turn a thick, rigid metal rod into thousands of meters of fine, flexible wire? With each strand perfectly engineered to carry a current? Today, we're showing you exactly how it's done. We're going inside a mega factory to uncover the complete step-by-step process. This is the art of electrical wire manufacturing.
Every high-conductivity electrical wire begins its journey deep within the earth.
Most wire starts as high-purity copper, which is still the gold standard for conductivity, though aluminum is also used.
The process starts long before the material reaches a cable factory, at mines where copper ore is extracted.
This ore is then crushed, smelted, and refined, often through a complex process called electrolytic refining,
which produces enormous slabs of nearly pure metal called copper cathodes.
The whole point of this intense refining is to achieve one thing: purity.
And get in the way of the electricity. These purified copper cathodes are then melted down in colossal furnaces at scorching temperatures. The molten copper, glowing like a miniature sun, is cast into a more manageable shape.
In most industrial settings, this happens through a continuous casting and rolling process. The
liquid metal is poured onto a casting wheel, where it solidifies into a long bar. This bar is immediately fed into a series of hot rolling mills, where powerful rollers shape and stretch the copper
into a uniform product known as a wire rod.
This wire rod, typically about 8 millimeters in diameter, is the real starting point for the manufacturing we're about to see.
The rods are wound into massive coils, some weighing several tons, and transported to the wire factory.
What arrives isn't just a coil of metal, it's a coil of potential, ready for its dramatic transformation. Once the massive copper rod coils arrive, they're staged for the most dramatic step in their transformation: wire drawing. The goal is simple in theory, but incredibly complex in practice. Stretch the thick 8 millimeter rod.
Tailored into a wire that's hundreds or even thousands of times thinner, without breaking it.
This all happens inside a powerful machine called a multi-die drawing machine.
The thick copper rod is uncoiled and fed in, starting its journey through a series of progressively smaller dies.
Each die is a small, precisely engineered disc, usually made from industrial diamond or tungsten carbide, to handle the intense friction.
The copper rod is forcefully pulled, or drawn, through the first die, which shrinks its diameter and increases its length.
Right after that, the now slightly thinner wire is pulled through a second, even smaller die.
This repeats again and again and again through a dozen or more dies in a single line.
With each pass, the wire gets thinner and longer, its volume staying the same as it's reshaped.
To manage the incredible heat and friction, the entire system is flooded with a constant stream of specialized lubricants and coolants.
These fluids are critical. They stop the wire from overheating and breaking, ensure a smooth surface finish,
And help the expensive diamond dies last longer.
The speed of this process is mind-blowing. As the wire gets thinner, its speed increases dramatically.
By the time it exits the final die at its target diameter, it can be traveling over 90 kilometers per hour.
A blur of gleaming copper being wound onto a large spool. The final diameter, or gauge, is meticulously controlled as it determines the wire's current capacity, resistance, and flexibility.
Through the art of the draw, a thick, heavy rod has been sculpted into a fine, precise, and incredibly long strand of wire. The wire drawing process is brilliant, but it's tough on the copper.
The physical stress of being pulled through the dies causes the metal to become work-hardened. Its internal crystal structure gets compressed and distorted, which makes the wire hard, brittle, and slightly less conductive. A hard, brittle wire is useless for most things. It would just snap when bent.
To get its flexibility and conductivity back, the wire has to go through a crucial heat treatment process called annealing.
Annealing is basically a controlled relaxation session for the metal.
The spools of freshly drawn wire are moved to an annealing station. In some factories, this means loading them into large furnaces. The spools are placed in a sealed chamber, which is often filled with an inert gas or steam to keep the hot copper from oxidizing.
The furnace then heats the wire to a specific temperature, usually between 350 and 600 degrees Celsius. This heat gives the copper's internal crystals the energy they need to reform and realign.
The stress from the drawing process is relieved, and a new, softer, more orderly structure is formed. After holding that temperature for a bit, the wire is cooled in a controlled way, often with a water quench, which locks in its new properties.
On more modern production lines, inline annealers are built right into the drawing machines.
The wire passes through an electrical field right after being drawn, which instantly heats it to the annealing temperature.
Before it's spooled, combining two steps into one.
The benefits of annealing are huge. First, it makes the wire much more ductile and tough.
This is what gives the final product its softness and flexibility, allowing it to be bent and routed through tight spaces without breaking.
Second, annealing restores the wire's optimal electrical conductivity. By relieving the internal stresses and creating a more uniform crystal structure, it creates a clearer, less resistive path for electrons. After this trial by fire, the copper is no longer just a thin strand of metal. It's a soft, flexible, and highly efficient conductor. For a lot of applications, a single, solid strand of copper isn't ideal.
A solid conductor is fine for wiring inside a wall where it won't move.
But it's not very flexible, and can break if it's bent or vibrated repeatedly.
To make a conductor that's both strong and super flexible, manufacturers use a process called stranding.
The idea is simple. Many thin wires are better than one thick one.
Spools of fine, annealed copper wire are brought to the stranding area. Here, huge, complex machines get to work. For a bunched conductor, a number of wires, maybe 7, 19, or more, are gathered together and twisted in a random pattern.
This creates a very flexible core, perfect for things like headphone cables.
For a more robust, stranded conductor, the process is even more precise. In a concentric stranding machine, a central wire runs straight down the middle, while a series of bobbins revolve around it. As the carriage spins, it lays the outer wires in a perfect helical pattern around the core.
This can be repeated with more layers, each twisting in the opposite direction of the one below it.
To build up very large and complex conductors.
The tightness of the twist, or lay length, is carefully controlled to get the right balance of flexibility and strength.
The main benefit here is a massive boost in flexibility and fatigue resistance.
Think of it like a rope versus a solid rod. And you can bend a rope thousands of times, but the rod would snap pretty quickly.
This makes stranded conductors essential for anything that moves, vibrates, or needs to be routed around corners.
From car wiring to industrial robotics cables.
The choice of strand count and pattern is a careful engineering decision, affecting not just the flexibility, but the cable's electrical performance too.
Through stranding, delicate threads of copper are unified into a single, resilient conductor.
Pure annealed copper is a fantastic conductor, but it has one weakness: oxidation.
When it's exposed to air and moisture, copper develops a surface layer of oxide that isn't very conductive
and can make it hard to get a good electrical connection.
And for jobs where long-term reliability and solderability matter, the bare copper needs an extra layer of protection. This is usually done through tin coating.
A thin layer of tin over the copper serves two purposes. First, it's a tough barrier against corrosion and oxidation,
which is critical in harsh environments with high humidity or chemicals. A tinned conductor will keep working reliably for years. Second, the tin layer makes the wire much easier to solder.
Since tin is a key part of solder, a tinned wire allows for faster, stronger, and more reliable connections, which is a huge deal in electronics.
There are two main ways to apply this coating. The first is hot dip tinning, where the stranded conductor is passed through a bath of molten tin. As the wire comes out, excess tin is wiped away, leaving a uniform coating. It's a fast and efficient method.
The second method is electroplating. This is a more controlled process where the conductor passes through a chemical bath containing dissolved tin.
An electric current is applied, causing the tin to deposit onto the copper wire in a very precise and even layer. Electroplating gives manufacturers extremely fine control over the coating's thickness. Not all wires get this treatment. Many common building wires are left as bare copper. But this step is a mark of high-quality manufacturing for electronics, automotive, and industrial cables.
The once bright orange copper now has a silvery shine, armored against the elements, and ready for its final layer.
At this point, we have a perfectly drawn, annealed, and stranded conductor. It's a great pathway for electricity, but it's also totally exposed and dangerous.
To turn it into a safe, usable wire, it needs to be wrapped in a non-conductive layer. This is the insulation, and the process used to apply it is called extrusion.
The process starts with the raw insulating material, which comes as small plastic pellets. The choice of material is critical and depends on where the wire will be used. Common choices include PVC for general-purpose cables,
Polyethylene PE for its great electrical properties, or cross-linked polyethylene XLPE for its high heat resistance in heavy-duty applications.
Manufacturers are also focusing more on sustainability, developing eco-friendly and halogen-free compounds. For extreme environments like aerospace, advanced polymers like PTFE or silicone rubber are used. These pellets are fed from a hopper into the extruder, which has a long, heated barrel with a large rotating screw inside.
As the screw turns, it pushes the plastic forward, and the combination of friction and heat melts it into a thick, uniform liquid.
It's vital that this molten polymer is perfectly smooth, with no bubbles, as any flaw could create a weak spot.
At the end of the extruder is a tool called an extrusion head.
The bare copper conductor is pulled through the center of this head at high speed.
At the same time, the molten polymer is forced out of the head and around the conductor, forming a perfect, seamless coating. It's the moment the conductor and insulator become a single, integrated wire.
Roots.
This quickly solidifies the polymer, locking it into its final shape. As the wire travels, laser micrometers continuously scan its diameter, measuring the insulation thickness in real time. This data is fed back to the extruder's controls, which make micro adjustments to keep the thickness within incredibly tight tolerances.
This precision isn't just for show. It's a matter of safety, ensuring the wire meets its voltage rating every step of the way. Many applications need more than just one insulated wire. A simple power cord, for instance, has at least 2 or 3.
To create these multi-core cables, the individual insulated wires are precisely assembled together in a process called cabling.
Pools of different colored wires, color-coded to identify live, neutral, and ground, are loaded onto another huge, rotating machine.
This cabling machine twists the insulated cores together in a controlled pattern. As they're twisted, soft fillers might be added to fill the gaps, which helps keep the cable's round shape and adds stability.
Sometimes, a binder tape is wrapped around the cores to hold them all together.
For many modern cables, especially those for data or used in environments with a lot of electrical noise, another layer is needed, a shield.
Electromagnetic interference (CLIVES) EMI intertrol can disrupt signals, so a shield acts as a barrier to block it.
There are 2 common types: a foil shield, which is a thin layer of aluminum that provides 100% coverage, and a braided shield, made from a woven mesh of fine tinned copper wires. Braided shields are strong and great at blocking lower frequency interference. Often, both are used together for maximum protection.
A bare drain wire is usually included in contact with the shield to make it easy to connect to a ground.
Finally, this whole bundle, cores, fillers, and shield, needs protection from the outside world. This is done with one last extrusion process.
Latular assemblyes. The entire assembly is fed through a large extrusion head and a final, tough outer layer, called the jacket.
This jacket is the cable's first line of defense against scrapes, moisture, chemicals, and sunlight. The material is chosen for durability, often a rugged PVC or a specialized thermoplastic.
As it exits the extruder, the finished cable is printed with its specs, manufacturer, wire gauge, voltage rating, and safety certifications.
It then goes through one last cooling trough, emerging as a complete, highly engineered product.
Creating a high-quality electrical cable is defined as much by rigorous testing as it is by manufacturing.
Throughout the entire journey, every component is subjected to a battery of tests to ensure it meets strict international standards for safety and performance.
This commitment to quality is what separates a reliable cable from a dangerous one.
The most advanced smart factories are embedding sensors to monitor variables like tension and temperature in real time. But for all factories, the final testing is what proves the quality. The testing starts with dimensional checks. As the wire is being insulated and jacketed, laser scanners continuously measure its diameter, point, and concentricity to ensure perfect uniformity.
Next come the most critical electrical tests. The conductor's resistance is measured to confirm the copper is pure and the gauge is correct.
Then comes the high voltage test, often called a spark test. Every meter of insulated wire is passed through a high voltage electrode. Thousands of volts are applied to the insulation surface.
If there's even a pinhole-sized flaw, a spark will jump to the conductor, instantly flagging the fault.
This ensures the insulation has no weak spots.
For finished multi-core cables, more tests are done to measure insulation resistance between conductors and check for shorts. These routine factory tests typically follow product-specific standards, like those from UL or IEC.
Mechanical tests are also essential to confirm the cable's durability. Samples are pulled until they break to measure their tensile strength and flexibility.
In cold bend tests, a cable is chilled to sub-zero temperatures and then bent to ensure the materials don't crack. For cables meant for constant movement, flexing tests might bend a sample back and forth tens of thousands of times to simulate its working life.
Finally, every batch of cable gets a unique code for full traceability. This means the manufacturer can track every single component and process parameter associated with that specific cable.
This data-driven approach to quality control is the final, crucial step in the process.
After passing the exhaustive gauntlet of quality control, the electrical cable is finally complete.
The last steps are all about getting it ready for the customer. The long, continuous length of cable is precisely wound onto its final packaging, maybe a small coil for retail.
A large plastic spool for contractors, or a massive wooden drum for infrastructure projects.
Automated coiling and spooling machines wind the cable neatly and under the correct tension to prevent damage.
The machines measure the length precisely, so each spool holds exactly what it's supposed to.
As the cable is wound, it's often printed with sequential meter or foot markings, so installers can easily measure lengths on site. The spools themselves are then labeled with all the key information: cable type, gauge, length, weight,
and all relevant safety certifications like those from Underwriters Laboratories Pot. Discounts, incentives, and
finally, the finished spools are wrapped in protective plastic to shield them from dirt and moisture during shipping. They're stacked on pallets, secured, and moved to the warehouse, ready for distribution.
From a massive raw coil of metal to a precisely engineered, fully tested, and perfectly packaged product, the transformation is complete.
And there you have it.
A solid rod of raw copper is pulled, heated, twisted, and wrapped through a dozen complex processes
to become a finished electrical cable, engineered for safety, reliability, and efficiency.
The next time you plug in a device or flip on a light switch,
maybe you'll remember the incredible journey of precision and power.
that went into creating the humble wire that makes it all possible. If you found this look inside the world of manufacturing fascinating,
be sure to subscribe and hit that like button.
let us know in the comments what other complex processes you'd like to see us uncover next.